In this video, we'll cover the problem maximum exchange rate. Your input is going to be a mapping. It maps from a particular currency, so this example is from US dollars, to various other currencies, so for example, euros. You're also given the exchange rate between those two currencies. So from US dollars to euros is 0.82. Similarly, from US dollars to pound, oops, I did not leave enough space, to the pound is 0.71 because of this exchange rate. Your job is to return the maximum exchange rate between two currencies, and those two currencies will be given as an input. So as an example, if you were given Canadian dollars to the Great British Pound, then one option is you can go from Canadian dollars, well, you have to go to US dollars, we know that for sure. So you go to US dollars, and remember your target is to get to the pound, GBP. So when you're at US dollars and you want to get to GBP, you can either go directly there, like this, or you can go to euros and then go from euros to the Great British Pound. But the maximum path is going to be going straight from US dollars to GBP to the Great British Pound. So we want to figure out what is the overall exchange rate here. So to go from Canadian dollars to US dollars, this one is actually let me erase these values and underline what we're doing. So Canadian dollars to US dollars is right here, 0.83. Oh, one thing I should mention is that the direction matters, right? You can see at the top, if you go from US dollars to Canadian dollars, it's 1.2, but it's not necessarily the same thing to go backwards. In fact, it's actually the inverse of it. So if we have 1.2 as our exchange rate to go from US dollars to Canadian dollars, then to go from Canadian dollars to US dollars, it's approximately the inverse, which is 1 divided by 1.2. So we're pulling this value here. Let me make this clear. This value, 0.83, is our exchange rate here. And then to go from US dollars to the pound, you can see that the value from right here is 0.71. So right here, we're doing 0.71. And I will just quickly make sure I don't mess this up. So if we do 0.83 times 0.71, that gives us 0.59 if we round to 2 decimal places. So over here, we can say, if you started with 1 Canadian dollar, then you would have 0.83 US dollars, and then you'd have 0.83 times 0.71 pounds in the end. So you get 0.59 is the overall exchange rate right here for this example, if we're going from Canadian dollars to the pound. One thing that's important here is that we multiplied our two exchange rates. That's something to realize with this question, is to get the overall exchange rate, you can multiply each of the individual exchange rates because they're sort of compounding on each other to give you the final exchange rate. All right, so that's why we get 0.59 as our answer for this particular set of inputs. Let me go ahead and erase what we've done so far, and then we can talk about an important concept with graphs. So with graphs in graph theory, there's the concept of a weighted edge, and that is demonstrated by this problem. So I've modeled our graph on the right-hand side of the screen, right here. And one thing you'll notice that's different from what we've seen before is that I have a label with each edge. So for example, with this edge going from Canadian dollars to US dollars, I have labeled it with 0.83. If we want to talk more abstractly, not specifically to this problem, but generally, we can call this a weighted graph, where each edge in the graph has a certain weight with it. And the weights can represent many different things. One example is exchange rates, like you can see here. Now, the terminology of a weighted graph doesn't really become that important in interviews, so I wouldn't stress too much about it. But I just wanted to mention that this is an example of a weighted graph. Okay, so Our goal with this question is to find the maximum exchange rate between the two input currencies. So we want to basically say, if we are starting at Canadian dollars, so I'll write an S right here for start, and our end is Great British Pound. What is the optimal way to do that? There are two ways we can do this. We can go from Canadian dollars to, how will I diagram? Yeah, I'll just diagram it like this. We can go from Canadian dollars to US dollars, like this. And then from US dollars to the pound. That is one valid option. The other option is to go from Canadian dollars, let's switch colors, is to go from Canadian dollars to US dollars. That's too similar of a color. I will use this color. Okay, from Canadian dollars to US dollars, and then from US dollars to euros, and then from euros to the pound. This is unfortunately a messy graph, but I'll erase this stuff in a minute. But these are two options. First option is go to Canadian dollars to US dollars to the pound. The second option is to go Canadian dollars to US dollars to the euro to the pound. Basically what we want to do is multiply all of the exchange rates in each of these paths and figure out which one is bigger. That's the core of how we're going to find the answer to this question. So, how do we know what algorithm or what approach we want to use to solve this question? Well, the important thing is that we are looking at full paths, right? There's one path through Canadian US dollars to US dollars to the pound. That's one path. And another path is Canadian dollars to US dollars to euros to the pound. Those are like two separate full paths, and we want to compare these. So to examine a full path, a depth first search is usually very helpful because a DFS can generate a full path because you go all the way down one path and then you stop and move back and consider other paths. Whereas a BFS is sort of level by level, but you're not really exploring a full path at one point in time. So DFS makes a lot of sense for this question. All right, so with that being said, the way we can do this is we can initiate a DFS from our start node, so from Canadian dollars here, and we basically just want to search all of the valid paths that allow us to get to our target currency, which is, in our case, the pound. And what we'll do is we'll just, every time we get to the Great British Pound, we'll say, all right, compare the exchange rate it took to get here versus our current maximum, and if we find something that's greater than our maximum, just go ahead and update it. So I want to outline our algorithm in the bottom left corner of our screen. So the algorithm is going to be like this. It's going to be a standard DFS with two nodes, but most of it is just going to be a typical DFS. Number one is that when we find ourselves at the end currency, we want to potentially check against our max value. So we'll say when we hit currency 2, which is our end currency, then check against the max. That's one of the differences between this DFS and a typical one. Check against max is what I should write here. The second difference has to do with how we calculate the overall exchange rate. So we know that we can multiply the individual exchange rates to get that. So maybe if we start at Canadian dollars, we can keep some sort of like current exchange rate. I'll just write cur here. And we start DFSing. So it's going to start at 1, but then we multiply by 0.83 to get to US dollars. So we say, all right, we're at 0.83. And then we multiply that by 0.71 to get to GBP, the Great British Pound. And that gives us 0.59. But now we want to move back to US dollars and say, okay, well, what if we took this approach of going to euros? Well, then we have to like divide by 0.71 and like to go backwards, which is not that intuitive, and then multiply it, like divide by 0.71 to get back to 0.83, and then multiply that by 0.82, and it gets like kind of confusing that way. The reality is that each node should have its own information. At US dollars, we can track, what was the exchange rate it took to get from our start currency to US dollars, the current currency. So the way we can do this is using an approach that we've seen many times before. What we'll do is whenever we put a node into our stack for a DFS, we will also put the exchange rate from the start currency to that currency with it. So let me write that here, and then I'll show you what I mean. So I'll just write store exchange rate so far with each currency, right? So far in the stack is what I'm referring to. So with, I'll just write it out, with each currency in the stack. All right, so as an example, the way we would do this is, I'll do this on the bottom right corner. So we'll have our stack here. And we're going to start by putting our, for now I'll just diagram it using a subarray like this, but you don't have to necessarily do this. You could use many different things based on the language you're using. But the first thing you're going to put is the start currency, which is Canadian dollars. I should leave space. Canadian dollars, and obviously its exchange rate with itself is just 1 because you can exchange 1 Canadian dollar for 1 Canadian dollar, and that's no value lost. Then we remove that currency, so we remove this out, and we say, all right, the only path we can follow is to go straight to US dollars. So if we do that, then we multiply by 0.83. So what we'll do now is we're going to put something on our stack that's going to contain US dollars, and we're going to pass the exchange rate to get from our start currency, which is Canadian dollars, to that current currency, which is US dollars. So that's just going to be 1 times 0.83, which is just 0.83. So we can put this here. Then that's the only neighbor of the Canadian dollar. So in terms of our graph, so we can pull out US dollars here and then explore the path if we went down to the pound. And in that case, we would put, the pound here, and we will take our 0.83 because that was how we got to US dollars, which was the previous node, but multiply that by the exchange rate from US dollars to the pound. So multiply it by 0.71. So here we're putting 0.83 times 0.71 as our exchange rate, which should just be 0.59. I'm not going to continue through all of it, but this covers the general idea of how this works, where each element in our stack is going to contain the exchange rate to get from the start currency to that particular currency. That's how we're going to handle this question. And one last note I should mention here, I'll put it on the bottom left, is that we also need to track what nodes we've visited before, because we have bidirectional edges, right? You can go from the pound to euro and back to the pound and back to the euro. So you can get in this infinite loop if you're not tracking what you've visited. So I'll just write here, we want to track what we've visited before and be careful about that. Okay, now we can talk about the complexity of this solution. So we will initially define our variables. I'll do that. We're a little low on space, so I'll do it right here. So we'll say V is going to be the number of vertices in our graph, which is also just the number of currencies that we have. And E is the number of edges in our graph, which is given based on the mapping. So our time complexity is going to be O of V plus E, because we are executing a DFS. Our space complexity is going to be O of V. So for our time complexity, we know that with a DFS, we are searching all paths. So it is certainly possible that we explore the entirety of our graph, which means, first of all, every vertex is pushed onto the queue at some point in time. So that's V vertices times O of 1 to push on, sorry, I said push onto the queue, push onto the stack because we're using a DFS. That's O of 1 for pushing onto a stack, and times V because they're V vertices, so that's O of V. For each currency that we touch, we are going through all of its edges, which means that in total, we're going through all of the edges. So we have V plus E as our overall time complexity. In terms of our space complexity, there are a couple things that are relevant here. First is the maximum size that our stack is going to take in the worst case scenario. You can imagine if we had a graph that was just like a line, if it's like one node goes to another node, that goes to another node, that goes to another node, like this, then the entire graph would be on the stack at one point in time. So that gives you O of V, because however many vertices you have, they can all be on the stack at the exact same time. Additionally, we are storing visited information right here on the bottom left corner of the screen. That could also, in the worst case scenario, contain every single vertex if we do traverse through the whole graph. So in that scenario, we also get O of V for our space complexity. All right, that's all for the approach. So let's go ahead and switch over to the implementation. Now, let's see an example of how to solve this question in JavaScript. So to get us started, you can see that there is the Q class that we have access to. We don't need it in our case because we're using a DFS, but it's there if we need it. Other than that, I have our function defined. And since we're now using interview-based, I don't actually need to manually define a test. We can just run our code and submit code later. So the way we want to handle this question is we want to grab the maximum exchange rate and set it based on our DFS. Inside of our DFS, we're basically going through our currencies and tracking what is the exchange rate so far. And whenever we find that we are at our end currency, then we compare versus the maximum. So let's start by creating a variable called max exchange rate. And initially, I'm going to set this to be negative infinity. So we can just do this. The reason I'm doing negative infinity, this is a pretty standard thing with maxes, is just so that if we compare anything versus negative infinity, that thing will always be greater than negative infinity, so we'll just overwrite it. Similarly with mins, you can start them out as positive infinity. All right, I'm also going to create a new set to track our visited elements because we mentioned we don't want to get in an infinite loop since we do have bidirectional edges, even though they are separate, right? Like to go from A to B is one edge and to go from B to A is a different edge with a different weight. Okay, now we can do some of our standard DFS stuff. So we create our stack. We're going to push our initial element onto the stack. Now, remember that each element on the stack is not just a currency, but it is also the exchange rate so far. So I will use an array like this. So I'll pass currency 1, which is our start currency from here. Currency 2 is our end currency. And we'll also pass 1 because the exchange rate from a currency to itself is just 1, as we discussed in the approach. All right, now we want to say iterate so long as the stack has elements in it. And what do we want to do in here? Well, we want to say currency, or let's say current currency, and exchange rate so far is going to be, man, I can't type right now, is stack.pop. This is using some destructuring. This is unfamiliar to you. I will translate it quickly into normal JavaScript without destructuring. So basically we're saying grab the node by popping off the stack, say current currency is going to be node at 0, and exchange rate so far is going to be node at 1. They're doing the same thing. This is just some nicer syntax for that. Okay, we pop off the stack. We know we want to process a node. We'll come back to it. We want to grab the neighbors of that node. So for US dollars, we want to see, okay, where can we go from here? So these are our 4 options. So we will say neighbors is going to be mapping at the current currency. Right, so our mapping says if you give me US dollars, I'll give you this array right here. Then what we can do is we can say iterate over all of our neighbors. And for each of them, what do we want to do? One thing I do want to mention is that it is guaranteed for this question that every currency is present in the input. So you're not going to have is present as a key in the input, to be more precise. So you're not going to have a currency that like appears in one of these but isn't a key. Sometimes that does happen, and if that's the case, then you need to handle that explicitly because, you know, the current currency might not be a valid key in mapping, and just make sure you check if neighbors was undefined. But for this problem, you don't have to because it is guaranteed that every currency that you are dealing with will be one of the keys in the mapping. So we will actually come back. No, we can do this now. So what we want to do is we want to push onto the stack this new neighbor. But to be clear, a neighbor is not a currency. It's this array because it's each element of our bigger array. So it's going to be an array that contains a currency and an exchange rate for that currency. So I'm going to destructure out those values. So we'll say neighboring currency, and neighbor exchange rate is going to be the neighbor. I'm just grabbing these values out from neighbor. Again, if you're not familiar with destructuring, I will translate that. So we'll say neighbor node is going to be, actually no, this is the neighbor itself. So we can just say neighboring currency is going to be neighbor at 0, and neighbor exchange rate is going to be neighbor at 1. That's all I'm doing on line 64 here. Okay, Now, what we want to do is we want to push the neighboring currency for sure onto the stack. And what do we do with the exchange rate? Well, let's say we are going from Canadian dollars to the British pound. And so far, what we've done is gone from Canadian dollars to US dollars. So we know the exchange rate so far was 0.83. Now we're about to push GBP onto the stack. What we want to do is say, take the currency it took, the exchange rate it took to get to US dollars from our start of Canadian dollars, which is 0.83, and then sort of add to it this new exchange rate, which is going to be US dollars to GBP, which is 0.71. And the way we combine currencies is we multiply them. So what you're going to do is take the exchange rate so far to reach the current currency, and then multiply it by the neighbor's exchange rate. So let me write that right here. It's going to be exchange rate so far times neighbor exchange rate. So you can think about it as, let's say there's like 5 steps to get from the start to this neighbor. Exchange rate so far is saying, okay, account for the first 4 steps to get to like position 4. And now we need to add the exchange rate to go from 4 to 5. This is important. This makes sure that we're storing the neighbor currency, which is easy, but we're also storing the exchange rate to get from our start currency to that neighbor currency with it, which is very important. Okay, so that allows us to push onto the stack. We have sort of the structure of our DFS setup. Let's also make sure in the end that we are returning our max exchange rate. All right, now we want to figure out how we process individual nodes. So the first thing is, how do we know that we're done? Well, the way that we know that we're done exploring a particular path is when we hit our target node, which is going to be currency 2. So the first thing we can say is if we hit the end, so if currency is equal to currency 2, then what do we want to do? Well, in that case, we want to compare versus our max exchange rate. So in that case, the exchange rate so far is really a full exchange rate to get from currency 1 to currency 2. So we want to see, is this better than the max that we already have? So we'll say max exchange rate is going to equal the max of 2 values. The first is going to be what it already is, and the second is going to be exchange rate so far, which is just the exchange rate for this particular path. If you haven't seen this before, this is equivalent to saying if exchange rate so far is greater than max exchange rate, then say that max exchange rate equals exchange rate so far. These are basically the same thing. This is just a shorter way to do it. And the way it's working is saying, take this max exchange rate variable and set it to be whichever is greater of 2 values, either what it already is or this value that we potentially want to overwrite with. Okay, we can get rid of this. All right, so we know that if we find our end currency, we want to update our max exchange rate. What else do we want to do? The other thing that we have to track is we don't want to get in an infinite loop. So whenever we do hit a node, the first thing we should do is say add it to our visited set, and we'll make sure that we never hit it again. Now we know that our currencies are unique, so we can just add the currency and nothing else. But we're not doing anything with this visited set right now, so it's not actually helping us at all, because fine, we add it to the visited set, but we still get in the infinite loop. So we also want to make sure that we skip nodes that we visited before. So we'll say if our visited set has the current currency, just go ahead and continue. You don't need to do any of our logic here. Now, the location of line 60 is very important here. The first thing is you cannot put it after line 62, because if you add the current currency to visited and then check if it's in visited, that'll always be true. So it must be before we add to the visited set. But also, we want to make sure that we check that we're at the end currency before we do this visited check, because if we are at the end currency, we may have visited it before, but that's okay, because we want multiple paths to the end currency, because we have to search all of them. Okay, so we can delete this line here. I believe this should be all, unless I missed something, but the general idea is we start with negative infinity as our max exchange rate. We have our visited set, we have our DFS where we track the currency and its exchange rate. We have our loop for our DFS, we grab out the current currency and its exchange rate so far to get to that current currency. If we're at our target currency, we just check against the max and potentially update it. if we've already visited our current currency, I should mention here that we need to continue. That's important because you don't want to do the rest of the logic. Once you've found your end currency, you just want to move on and say, all right, let's explore a different path. All right. Now you say, all right, if it's visited, move on, and then add it to visited so that we never process this particular currency or node again. Then you grab the neighbors using our map as the input. For each of them, you want to grab out the currency and the neighbor exchange rate. Then we push the neighbor currency, and this is the important part here, which is take the entire exchange rate so far, multiply by the neighbor's exchange rate, and push that onto the stack. And in the end, we return our max exchange rate. So let's go ahead and start by running our code to make sure that it works against this initial input. No, okay, so we're getting a reference error which says neighbor currency is not defined. Yes, okay, so here I've named it neighboring currency, here I've named it neighbor currency. It doesn't really matter which one we use. I'll just go ahead and use neighbor currency since we have that. Now if we run it, we get 0.589299. Okay, so you can see that it looks like we're getting the right answer, but it's not rounding appropriately. So this is an important point. The problem statement says return your answer rounded to 2 decimal places. So let's go ahead and do that. I'm actually going to write a separate function for that just because it's not that elegant. So we'll say round to 2 decimal places, and this is going to take a number and then do something to it. So I'll just do this because we can return in one line. Actually, no, it's okay. Just in case you're not familiar with an implicit return, I'll do it like this. Now what we're going to do is we're going to say math.round, and this is going to look a little bit confusing, but here's what we do. Something like epsilon, and then divide that by 100. So what's happening? No, we want to round this and then divide by 100. So this is how we're going to return to round to 2 decimal places. It's actually not 100% foolproof. There are several ways you can do this in JavaScript, and most of them aren't that great. So what we're doing here is we're taking the number, multiplying by 100, then we're adding number.epsilon. So number.epsilon is the difference between 1 and the smallest number that is greater than 1 that a computer can store. This has to do with like how floating point numbers are stored in a computer. Basically, I'm not going to go too much in the details here of how this works. I encourage you to look up how to round to 2 numbers in JavaScript, and there's a lot of stuff you can read that goes into more detail here. But basically, this is how we are going to do it. So we can go ahead and round to 2 decimal places and then pass in our output. Pass in our max exchange rate, and then that gives us our output. So if we run our code now, looks like we're getting the right answer. Let's see if we submit code. Looks like we pass all of the test cases here. So we can look through them and make sure every single time we have our green check mark. Looks like things are pretty good and our algorithm seems to be working. All right, let's talk about the complexity of our solution right here. So we'll start by defining v to be the number of vertices, which is also equal to the number of currencies. And e is going to be the number of edges. So our time complexity is O of v plus e, our space complexity is O of v. We see that every node could be pushed onto the stack at some point in time, which is why we get dependence on v for our time complexity. And we're processing every edge from line 75, every edge for that particular node. And we're doing this potentially for every node, so in total we have this dependence on e for our time complexity, so we have v plus e. For our space complexity, it's O of v, because our visited set could potentially contain all of the currencies if we explore the whole graph. And there's also the reasoning, which is that if we had a single sort of linear graph where we one node to another node to another node and so on, then our stack could, in the worst case scenario, and at one point in time, contain all of the nodes in our graph, so all of the vertices in our graph. So we get the O of v space complexity. All right, that's all for this video, and I'll see you in the next one.